Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're going to cover Chapter 9 for our MCAT Organic Chemistry playlist, and this chapter is titled Carboxylic Acid Derivatives. In this chapter, we're going to explore the following objectives. First, we're going to describe the main classes of carboxylic acid derivatives, specifically amides, esters, and anhydrides, and we're going to understand how they're related to carboxylic acids. Next, we will discuss key reactivity principles, including the relative reactivity of different derivatives, the impact of steric effects, electronic effects, and the role of ring strain in cyclic derivatives. Finally, we will explore important nucleophilic acyl substitution reactions, focusing on anhydride cleavage, transesterification, and hydrolysis of amides. Something you're going to notice in this chapter is the reiteration of some of the content we briefly covered in the last chapter. With that introduction, let's go ahead and get started with the first objective. Amides, esters, and anhydrides are all classified as carboxylic acid derivatives. What this means is that all of these functional groups are formed by modifying a carboxylic acid, typically through a condensation reaction. In a condensation reaction, two molecules are joined together, and a small molecule, often water, is lost as a byproduct. Each of these derivatives maintains the core feature of the carboxyl group, which is a carbon atom that's double bonded to an oxygen atom. This is known as a carbonyl. But what's different is that the hydroxyl group that's attached to the carbonyl carbon, that's going to be replaced by another group. Let's take a look at each type one by one. First, we have amides. An amide is formed when the hydroxyl group of a carboxylic acid is replaced by an amino group, specifically a nitrogen atom that's bonded to hydrogen atoms or alkyl groups. The general structure of an amide is shown here. So again, you'll notice we have a carbonyl group that's directly bonded to a nitrogen atom. Next, there's esters. An ester is formed when the hydroxyl group of a carboxylic acid is replaced by an alkoxy group, meaning an oxygen atom that's bonded to a carbon group. So the general structure of an ester is a carbonyl group directly bonded to an oxygen, which is in turn bonded to another carbon atom. Finally, anhydrides. An anhydride is formed when two carboxylic acid molecules condense together and they lose a molecule of water. The resulting structure features two carbonyl groups connected by a single oxygen atom. So all of these derivatives, amides, esters, and anhydrides, they're connected by a common origin. They are derived from carboxylic acids through condensation reactions that modify the group attached to the carbonyl carbon. Now let's focus a little more specifically on amides, and let's start with their naming and their special types. Amides are compounds with the general formula R, CO double bonded, and R2, where R groups attached to the nitrogen can be either hydrogen atoms or alkyl substituents. When naming an amide systematically, we're going to start by naming the parent carboxylic acid, and then we're going to replace the oic acid ending with amide. For example, if we begin with ethanoic acid, this is a 2-carbon carboxylic acid, and then we convert it into an amide, the resulting compound is named ethanamide. But what if, instead of having two hydrogens attached to this nitrogen, we had an alkyl group that's attached. How would we go about naming this compound? Well, if there are any alkyl groups attached to the nitrogen atom, we name them as substituents. These alkyl groups, they're going to be placed at the very beginning of the compound's name, and they're going to be denoted with the prefix N to indicate that they're attached to the nitrogen and not to the main carbon chain. So for instance, if a methyl group is attached to the nitrogen atom, we call it N-methyl before the rest of the molecule's name. Now let's briefly talk about a special category of amides known as lactams. Lactams are cyclic amides, meaning that the amide functional group is incorporated into a ring structure. The size of the ring and the position of the nitrogen atom relative to the carbonyl carbon determine the name of the lactam using Greek letters. So first we can have a beta lactam. This is a four-membered ring with the nitrogen located on the beta carbon relative to the carbonyl group. Then we can have a gamma lactam. This is a five-membered ring with the nitrogen located on the gamma carbon. A delta lactam is a six-membered ring with the nitrogen located on the delta carbon. The Greek letter corresponds to the number of carbon atoms separating the carbonyl carbon and the nitrogen atom. And lactams are biologically significant structures. For example, beta lactam form the core structure of penicillin and related antibiotics, where the strained four-membered ring makes the molecule highly reactive. Now let's turn our attention to the second major class of carboxylic acid derivatives, esters. Esters are formed by the dehydration synthesis between a carboxylic acid and an alcohol. In other words, a molecule of water is removed when the hydroxyl group from the carboxylic acid and the hydrogen atom from the alcohol combine, and that allows those two molecules to join together. Esters are named systematically by identifying two parts. The first part is the esterifying group, which comes from the alcohol. This group is named first, and it's written as a separate word. The second part is the acid portion, which is named by replacing the oic acid ending of the parent carboxylic acid with OA. Let's walk through the examples that are shown. In the first structure, we have an ester that's derived from ethanol and ethanoic acid. So the alkyl group from the ethanol is ethyl, and the acid part, ethanoic acid, becomes ethanoate. Therefore, this ester is named as ethyl ethanoate. In the second structure, we have an ester formed from isopropanol and butanoic acid. The alkyl group from isopropanol is isopropyl. The acid part, butanoic acid, it becomes butanoate. So the name of this ester is isopropyl butanoate. Now let's talk about how esters are actually formed in the lab, specifically through a reaction called Fischer esterification. Under acidic conditions, mixtures of carboxylic acids and alcohols can react to form esters. And this reaction is driven by protonating the carbonyl oxygen of the carboxylic acid, and that makes the carbonyl carbon more electrophilic and thus more susceptible to attack by the alcohol nucleophile. So here's the general mechanism. First, in the presence of an acid catalyst, often sulfuric acid, the carbonyl oxygen of the carboxylic acid is protonated. This increases the positive character of the carbonyl carbon, making it more attractive to nucleophiles. Next, the alcohol attacks the carbonyl carbon, breaking the double bond and forming a tetrahedral intermediate. Then, one of the hydroxyl groups in the intermediate can be protonated to form water, which is a good leaving group. The molecule then eliminates the water and it reforms the carbonyl bond, resulting in the formation of the ester. So the overall products of this reaction are an ester and a water molecule. With that in mind and moving forward, esters can exist in cyclic forms, and when they do, they're called lactones. Lactones form when a hydroxyl group within the same molecule reacts with a carboxylic acid group, closing the structure into a ring and therefore creating a cyclic ester. Lactones are named similarly to lactams, using Greek letters to indicate the position of the oxygen relative to the carbonyl group. Alpha acetolactone is a 3-membered cyclic ester. Beta propiolactone is a 4-membered cyclic ester. And gamma butyrolactone is a 5-membered cyclic ester. These cyclic structures are important because they often show up in natural products, including flavors, fragrances, and some biologically active molecules. Finally, let's talk about an important biological example of esters, triacyl glycerols. These are also known as triglycerides, and they are the storage form of fats in the body. They're formed by the esterification of 3 long-chain carboxylic acids, often called fatty acids, with 1 molecule of glycerol. Glycerol is a 3-carbon molecule with a hydroxyl group attached to each carbon. Each hydroxyl group of glycerol undergoes a condensation reaction with a fatty acid, and that forms 3 ester bonds and results in the triacyl glycerol structure. Now, let's look at how triacyl glycerols can be broken down, specifically through a reaction known as saponification. In saponification, a triacyl glycerol reacts with a strong base, typically sodium hydroxide, under heat. The ester bonds are then cleaved in a process called base catalyzed hydrolysis. So each ester bond is broken, and that yields 1 molecule of glycerol and 3 molecules of fatty acid salts. The fatty acid salts are composed of carboxylate anions paired with sodium cations. So in other words, soap. Therefore, saponification of triacyl glycerols produce soap molecules and glycerol as products. Now let's move on to the final class of carboxylic acid derivatives that we're going to discuss in this chapter, anhydrides. Anhydrides are the condensation dimers of carboxylic acids. In other words, an anhydride forms when 2 carboxylic acid molecules combine, and in that process, 1 molecule of water is eliminated. Let's begin with nomenclature. Anhydrides, they can be symmetrical or they can be asymmetrical, and the naming rules depend on the distinction. So for symmetrical anhydrides, both sides of the molecule are derived from the same carboxylic acid. To name them, simply take the name of the original carboxylic acid and replace the word acid with anhydride. For example, if the carboxylic acid is ethanoic acid. The resulting symmetrical anhydride is called ethanoic anhydride. If the acid is succinic acid, which is a dicarboxylic acid, then the corresponding anhydride that's formed is succinic anhydride. Now, what about asymmetrical anhydrides? For asymmetrical anhydrides, each side of the molecule comes from a different carboxylic acid. In this case, the naming rule is to list both acid components in alphabetical order, followed by the word anhydride. So for example, if your two acids are ethanoic acid and propanoic acid, then the compound that's formed is named ethanoic, propanoic, anhydride, with the names ordered alphabetically. Now let's go over how anhydrides are formed. The most common method is by the condensation of two carboxylic acids. So in this reaction, the hydroxyl group from one carboxylic acid and a hydrogen from the hydroxyl group of the other acid are removed. So these two atoms, a hydroxyl and a hydrogen, they combine to form water, which is released from the reaction. What remains is a structure in which two carbonyl-containing portions are connected by a single oxygen atom. And this is the defining feature of an anhydride. This reaction is typically driven by heat, and in many cases, it requires removal of water to push the equilibrium forward. In addition to open chain anhydrides, there are also cyclic anhydrides. Certain molecules containing two carboxylic acid groups on the same molecule, especially when they're close together, can form cyclic anhydrides simply by heating. A great example is orthothalic acid. This compound contains two carboxylic acid groups that are on adjacent carbons of a benzene ring. When heated, this molecule undergoes intramolecular condensation, where one carboxyl group donates a hydroxyl and the other donates a hydrogen. Water is eliminated, and the result is a five-membered ring anhydride structure called phthalic anhydride. This type of transformation is particularly common with dicarboxylic acids, where the geometry favors ring closure, and it often proceeds with heat alone. Now that we've introduced the major classes of carboxylic acid derivatives, we're ready to move into our second objective for this chapter. Here we're going to talk about reactivity principles. Understanding the reactivity of carboxylic acid derivatives is important because it allows us to predict how these molecules will behave in different chemical reactions, particularly nucleophilic acyl substitution reactions. So first, let's discuss the general trend of reactivity among these three major classes. Amides are going to be the least reactive of the three. Then esters are slightly more reactive, and they're approximately tied with carboxylic acids. But anhydrides, those are the most reactive. So this ordering from amides to esters to anhydrides, it's determined by several important factors that influence how easily the carbonyl carbon can be attacked by a nucleophile. Let's now walk through the major factors that influence the reactivity of carboxylic acid derivatives. We're going to begin with steric hindrance. Steric hindrance refers to the physical crowding of a reactive site by nearby bulky groups. When large substituents are positioned around the carbonyl carbon, it becomes more difficult for an incoming nucleophile to approach and attack that carbon. As a result, the reaction can slow down, or it may not proceed at all. It's important to clarify that this concept is not about electronic effects. It's purely about physical space and spatial interference. In synthesis, chemists sometimes use this principle to their advantage by attaching protecting groups to shield reactive sites so that they may prevent unwanted side reactions. This deliberate use of bulk is based entirely on steric hindrance. Next, we consider induction. This is an electronic effect, and it involves the pulling of electron density through sigma bonds due to differences in electronegativity between atoms. In the context of carbonyl chemistry, electronegative atoms near the carbonyl can pull electron density away from the carbonyl carbon, and that's going to make the carbon more partially positive and therefore more electrophilic. So the more electrophilic the carbonyl carbon, the more likely it is to be attacked by a nucleophile. Let's take two examples. In anhydrides, the carbonyl carbon is adjacent to an oxygen atom that bridges to a second carbonyl group. This bridging oxygen is quite electronegative, and the additional carbonyl group also withdraws electron density through induction. So together, these effects greatly enhance the partial positive character of the carbonyl carbon, making it highly electrophilic and more reactive. In contrast, in amides, the carbonyl is bonded to a nitrogen atom. Nitrogen is less electronegative than oxygen, and it has a lone pair that can delocalize into the carbonyl via resonance. This resonance donation pushes electron density towards the carbonyl carbon and it stabilizes it. So that's going to decrease its electrophilicity and its reactivity. So compared to oxygen in anhydrides, the nitrogen in amides does the opposite. It reduces the carbonyl susceptibility to nucleophilic attack. What about conjugation? Conjugation refers to the presence of alternating single and double bonds in a molecule. This alignment allows for electron delocalization across multiple atoms, which can stabilize both the ground state of the molecule and the high energy transition state that's formed during a reaction. In some cases, conjugation can spread out the electron density and make the carbonyl less electrophilic. However, in other cases, conjugation can stabilize the transition state, which lowers the activation energy for the reaction. In general, carbonyl-containing compounds that are conjugated to other electron withdrawing groups or extended pi systems, they're going to exhibit, more likely than not, enhanced reactivity under the right conditions due to that transition state stabilization. Finally, we need to talk about ring strain, especially in cyclic derivatives. Small ring systems contain significant angular strain because their bond angles deviate substantially from ideal values. And this strain makes the molecule higher in energy and therefore more reactive because the system is energetically eager to break the ring and relieve that strain. So for this reason, cyclic derivatives with high ring strain tend to undergo nucleophilic attack more readily than their open chain counterparts. With that, we can move into our final objective for this chapter, which is studying the nucleophilic acyl substitution reactions of carboxylic acid derivatives. We'll begin by looking at how anhydrides react with different nucleophiles to form other types of compounds. Anhydrides, being highly reactive, can easily undergo nucleophilic attack at the carbonyl carbon, leading to cleavage of the anhydride and formation of new products. Let's walk through the different substitution reactions involving anhydrides one by one. First, let's consider what happens when an anhydride reacts with ammonia. In this reaction, the ammonia acts as the nucleophile. It attacks the carbonyl carbon of one of the carbonyl groups in the anhydride, and that pushes the electrons up onto the carbonyl oxygen, and it forms a tetrahedral intermediate. In the intermediate, the oxygen now carries a negative charge, and the nitrogen from ammonia is temporarily attached to the carbonyl carbon, and it carries a positive charge. To restore stability, the intermediate collapses by reforming the carbonyl double bond and ejecting the leaving group, which is the remaining carboxylate portion of the anhydride. So this step releases a carboxylate anion, and it leads to the formation of an amide. Finally, the carboxylate anion that was released picks up a proton from the ammonium species, which regenerates a neutral carboxylic acid. So the overall products of this reaction are an amide and a carboxylic acid. Now let's look at what happens when an anhydride reacts with an alcohol, let's say methanol, for example. This mechanism follows a very similar pattern. The alcohol acts as the nucleophile, and it attacks the carbonyl carbon of the anhydride. This is going to push electrons onto the carbonyl oxygen, and again forms a tetrahedral intermediate. In this intermediate, the oxygen from the alcohol now carries a positive charge because it has added to the carbonyl. The structure then collapses by reforming the carbonyl bond and ejecting the leaving group, which is again a carboxylate anion. The carboxylate anion can then abstract a proton from the positively charged oxygen group, and that regenerates a neutral molecule. So as a result, the products of this reaction are an ester and a carboxylic acid. Specifically, the ester is formed by the combination of the alcohol and one carbonyl unit from the anhydride. Finally, let's examine what happens when an anhydride reacts with water. In this case, water serves as the nucleophile. Water attacks the carbonyl carbon. We break this double bond, and the electrons are dumped on the oxygen. And we form a tetrahedral intermediate where the oxygen from the carbonyl carries a negative charge, and the oxygen from the water that has attached carries a positive charge. Then the intermediate collapses by reforming the carbonyl bond and expelling the carboxylate anion. After proton transfer from the attacking water molecule, the expelled carboxylate anion is protonated, and this results in the formation of two molecules of carboxylic acid. So the hydrolysis of an anhydride, meaning its reaction with water, produces two equivalents of carboxylic acid. So in all three cases that we covered, whether the nucleophile is ammonia, an alcohol, or water, the fundamental mechanism is nucleophilic attack on the carbonyl carbon, formation of a tetrahedral intermediate, and then the subsequent collapse of the intermediate to eject a leaving group and restore the carbonyl functionality. The identity of the nucleophile then determines whether the product is an amide, an ester, or additional carboxylic acids. And this set of reactions really highlights why anhydrides are considered highly reactive derivatives. They readily undergo nucleophilic attack, and they can be transformed into a wide variety of important functional groups under mild conditions. Let's move on to another type of substitution reaction called transesterification. In this, one ester is converted into another ester by reaction with an alcohol. So in this process, the alcohol acts as the nucleophile, and it attacks the carbonyl carbon of the ester. This leads to the displacement of the original alkoxy group and replacement with the new alcohol group. So for example, in this reaction that's shown here, we start with an ester molecule and it reacts with ethanol. The ethanol nucleophile attacks the carbonyl carbon and it forms a tetrahedral intermediate where the carbon is temporarily bonded to two oxygen groups. One of the oxygen groups, specifically the original esterifying group, then leaves and the carbonyl double bond is reformed. So as a result, we generate a new ester now containing the ethanol-derived group and release the original alcohol as a byproduct. So this kind of reaction is important in both biological and industrial contexts. So in biological systems, they are part of processes like triglyceride metabolism, and in industry, they're key in the production of biodiesel. Now moving on, let's discuss the hydrolysis of amides. Amides can be hydrolyzed under highly acidic conditions to regenerate the corresponding carboxylic acid. And this reaction proceeds through a nucleophilic acyl substitution mechanism that's similar in principle to what we've already seen with other derivatives. This reaction begins with the protonation of the carbonyl oxygen. This is going to increase the electrophilicity of the carbonyl carbon, which makes it more susceptible to attack by water. Water, acting as a nucleophile, attacks the carbonyl carbon, which pushes the electrons up onto the oxygen atom and forms a tetrahedral intermediate. In the intermediate, one of the oxygen atoms is positively charged, and the nitrogen atom is neutral. This structure then rearranges. There's a proton transfer that occurs to convert the amine leaving group into a better leaving group. Then the tetrahedral intermediate collapses as the carbonyl reforms and the ammonia is expelled. Finally, deprotonation of the carbonyl oxygen yields the neutral carboxylic acid product. And we also have ammonia as a product. So the overall result is the conversion of an amide into a carboxylic acid and ammonia. And this hydrolysis reaction is typically slow under neutral conditions, but it can proceed much more readily in strongly acidic environments where the carbonyl activation and protonation steps are favored. So in summary, nucleophilic acyl substitution reactions allow us to interconvert different carboxylic acid derivatives. We have completed this lecture. I hope it has been helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.